When your data's got a trend, but you're feeling lost, let's fit a line and see what it costs. Hello, welcome to Algo's Talk. Today we are diving into the fascinating world of linear regression. It's going to be a great journey, so let's get started. For this, we'll be using 5 randomly selected data points from the California housing dataset, which is available for free through scikit-learn. It's a great way to see linear regression in action with real world data. To make things clearer, I'll focus on just one feature, house age, to predict our target variable. This will help us see how linear regression really works. We have got house age on the x-axis and property valuation, our target variable, on the y-axis. The first data point shows a house age of 12 years with a valuation of 2.268 units. Similarly, I have plotted all 5 data points on the graph. Now, to predict the target value on the y-axis based on house age on the x-axis, we can use linear regression with the information from these 5 data points. But how do we choose the best line to represent the information we have? Our objective is to find a line that comes as close as possible to all the data points, minimizing the distance between the line and each point. Okay, what does that really mean? Let's focus on one data point to make it clearer. The actual value of the data point for x equal 46 is 2.294, and according to the line, the predicted value for x equals 46 is 0.5. So the difference or residual is calculated as predicted value minus actual value. Or we can express it as e equals y hat minus y. So in this case, the residual is minus 1.795. Similarly, we can compute the residuals for all 5 points we have. If we sum all the residuals from these points, we get the basis of our target function, which we need to minimize. When summing the residuals for all the points, we first square each residual. This way, negative errors don't cancel out positive ones. So, effectively, our error function, known as the residual sum of squares or RSS, is calculated as the sum of the squared differences between the observed values and the predicted values for all n data points. In our case, with 5 data points, the residual sum of squares is calculated as 4.45 minus 2.27 square plus 1.33 minus 2.25 square and so on. The residual sum of squares in our case is approximately 14.34. Now, focusing on the line, the equation of a straight line is given by y equals mx plus c, where c is the intercept, which is the point where the line crosses the y-axis, and m is the slope of the line, which represents the rate of change of y with respect to x. Since we have plotted the line and know its slope and intercept values, and we have also calculated the residual sum of squares, we can organize these values in a table. To understand the impact of these changes, let's fix the slope at a constant value and see how the RSS changes as we adjust the intercept. Dup, dup, dup. If we plot the residual sum of squares on the y-axis and the intercept values on the x-axis, we will observe a parabola-like curve. Linear regression aims to find the intercept value that minimizes the residual sum of squares. This means it seeks the point where the RSS is at its lowest, or where the slope of the curve is 0. Also, note that linear regression finds all the coefficients simultaneously. This means it will determine both the slope and intercept together, for example. In practice, it can also handle multiple features and find coefficients for all of them. After working through the calculations, we get the equation of the best fitted line as y is equal to 2.679 plus negative 0.02 multiplied by x, or equivalently target equals 2.679 plus negative 0.02 multiplied by house age. As we wrap up our discussion on linear regression, it is essential to address some key assumptions and challenges that come with this powerful technique. These assumptions are like the foundation of a house. If they aren't solid, our model might not stand strong. First, linearity. Linear regression assumes that the relationship between our dependent variable and independent variables is linear. This means that if we plot the data, it should ideally form a straight line. Here we have data that fits well with a linear model. The red line represents the linear fit, showing that linear regression works well when the relationship is indeed linear. In this case, the data follows a sinusoidal pattern, but the orange line from linear regression doesn't fit well. This tells us that linear regression alone won't capture a sinusoidal trend effectively. Here, the data follows a quadratic curve. The pink line from linear regression misses the curve, indicating that we might need a polynomial regression to fit this type of relationship. Finally, this data shows a logarithmic trend. The yellow line doesn't match the data well, suggesting that a logarithmic transformation or another model might be necessary. The errors or residuals should be independent of each other. This means the error from one data point shouldn't be related to the error from another. The left graph shows data with errors that are independent of each other. The points are scattered around the red linear fit line without any noticeable pattern, indicating that errors are random and not related to each other. The right graph shows data where the errors are correlated. The points deviate from the orange linear fit line in a systematic way, often in the same direction for several consecutive points. This pattern indicates that the errors are not independent, which can lead to problems in interpreting the model. Next, the variance of the errors should be constant across all levels of the independent variables. If errors spread out more at higher values, this is called heteroscedasticity. In the left graph, the variance of the residuals is constant across all values of x. This is the ideal scenario for linear regression, where the model's errors are evenly distributed around the fitted line. In the right graph, the variance of the residuals increases as x increases. This means the errors get larger at higher values of x. Heteroscedasticity can lead to inefficient estimates and biased standard errors, which can make hypothesis tests and confidence intervals unreliable. Our independent variables should not be too highly correlated with each other. High correlations can make it difficult to determine the individual effect of each predictor. The left plot shows a 3D scatter plot with the two independent variables x1 and x2 and dependent variable y. Since x1 and x2 are highly correlated, the points form a flat plane rather than a more dispersed cloud. This indicates that x1 and x2 are providing redundant information about y, making it difficult to determine the individual effects. The right plot shows a 2D scatter plot of x1 and x2. The points lie close to a straight line, which indicates a high correlation between x1 and x2. This high correlation is what creates multicollinearity in the regression model. For reliable hypothesis testing and confidence intervals, we assume that the residuals are normally distributed. The left plot is a histogram that shows the distribution of the residuals. If the residuals are normally distributed, the histogram should form a bell-shaped curve centered around 0. This is a quick visual check to see if the residuals approximate a normal distribution. The right plot is a QQ plot, which compares the quantiles of the residuals against the quantiles of a normal distribution. If the residuals are normally distributed, the points will lie approximately along the red reference line. Deviations from this line indicate departures from normality. In summary, while linear regression is a powerful tool for predicting and understanding relationships between variables, it is important to remember the assumptions and challenges we have discussed. By ensuring that our data meets these assumptions and being mindful of potential challenges, we can make more accurate and reliable predictions. Now, let's take a look at the residual analysis of our model. We observe that the residuals are randomly scattered with respect to the predicted values, which indicates that our model is fitting the data well. Additionally, when we examine the QQ plot, we see that the residuals fit the expected normal distribution quite nicely. Thanks for sticking with us to the end. I hope this video has helped you grasp the fundamental concepts of linear regression. If you are interested in diving deeper into the math or want to see how to implement it in Python, we have detailed explanations available in separate videos. Just check out the links in the description below. If you find this video helpful, don't forget to hit the subscribe button to stay updated with more content like this. Until next time, take care and keep learning.